Okay, so we're going to talk a little bit about using probabilities to find likelihoods of given genotypes and phenotypes. And so obviously we could do a Punnett square, and we can find out in your basic, your basic Punnett square, monohybrid cross, and this is F1 generation, capital P, small p, so two heterozygous. What are we going to get? We're going to get 1/4 of each of these things. But in terms of, so two things. One, the homozygous, 1/4. But these heterozygotes are essentially the same. So we could say there's a 1/2 chance, 1/4 plus 1/4 chance of getting the heterozygous. So we see that up here. The homozygous dominant, 1/4, heterozygote, 1/2, and homozygous recessive, 1/4. But what if we do a dihybrid cross of the F1s? We got capital P, capital Y, small y. Remember that in the F1 generation, everything is heterozygous. So, have this heterozygote for two traits versus this heterozygote for two traits. And we're looking at flower color and seed color. All of these F1s are going to be purple and yellow, but we see down here that some of them, some of the offspring, we're going to get the white, and we're going to get the green. So, all right, how do we figure out the these ratios? We know that it ends up being 9. 9 of them show the dominant in both. That is, 9 of them are going to be purple and yellow. 3 of them are going to be purple and green. 3 of them, so they're going to show one of the two dominant traits. 3 of them are going to be white. There's the recessive, and yellow. So 3 more are going to show one the other dominant trait, and just one, this guy over here, is going to show both recessive traits. It would be the white flower and green seed. And we could go through and find these one by one. Each one of these squares, there's going to be 16 squares, 4 here in a dihybrid cross. 16 squares. The ratio is going to add up to 16. And we could go through and find which are which, and add up the 16ths, and see how we get to 9/16 and 3/16. But we could do this a little bit of a different way. Let's take a look. So here's the example. We could go and look. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9. All those genotypes ended up with both dominant characteristics, and we did the same thing for the ones that had one dominant characteristic, and then the one that had both recessive characteristics. But you can make mistakes, and that could be time consuming. So here is an alternative way. We could make an ordered list, and I'm showing it right now, and then I'm going to delete it. And given that the recessive, the heterozygous individual, we can kind of count as one. So here's the homozygous dominant for both. That's only going to happen once out of the 16 squares. What homozygous dominant for one and heterozygous would be 1/4 for the homozygous dominant. Let's go back and look here again. How are we getting that 1/4? From the original simple one. We know that a homozygous dominant is going to have a 1/4 chance of happening. We know that a homozygous recessive is going to have a 1/4 chance of happening. And we know that if we add these two up, the odds of getting a heterozygous individual for any given trait is 1/2. So we just remember that. And then going back to our list then, in this case, we're getting 1 homozygous dominant and 1 heterozygous. That's going to be 1/4 chance of getting the homozygous dominant, 1/2 chance the heterozygous, which gives us 1/8. We keep doing this again and again. Homozygous dominant, heterozygous. That's going to be 1/4 for a homozygous dominant and 1/4 for the homozygous recessive. 1/4 times 1/4, 1/16 chance of getting that. Heterozygous, 1/2. Homozygous dominant, 1/4. And we see that, and we get 1/8. Heterozygous, 1/2 times 1/2 gives us 1/4. And so on and so on. At this point, we're just repeating this. It's going to be 1/2 every time we have a heterozygous option, and 1/4 times 1/4 chance for any homozygous option. And we didn't have to do 16. Let's just go through and see how this worked. If we do YY, there are going to be 3 options for the homozygous dominant. There's going to be YY and then homozygous dominant for the other trait. There's going to be YY and then heterozygous for the second trait. There's going to be YY and homozygous recessive for the what's called the homozygous dominant Y. So let's do the same thing for heterozygous for yellow. We're going to get homozygous and heterozygous and homozygous for the other trait. And so now we're down to the heterozygous for yellow, and we have homozygous dominant, again homozygous recessive for yellow, plus heterozygous, and homozygous recessive for yellow, and homozygous recessive for wrinkled or round. All right, and then again, so now once you have your ordered list, how did we do this? Start with homozygous dominant. There's going to be 3. There will be, for homozygous dominant, there would be homozygous dominant for round wrinkled, homozygous dominant for, or heterozygous for round wrinkled, and homozygous recessive, giving you wrinkled. And you just do that for the homozygous dominant situation, the heterozygous situation, and the homozygous recessive situation of the yellow-green. And then, again, the odds aren't too hard. 1/4 for any homozygote, 1/2 for any heterozygote. And we get these numbers up here. Now, we can go back, and it's I think, easier to figure out, A, which of these are yellow, which of these are yellow round, which of these are yellow wrinkled, which of these are green round, and which of these are green wrinkled, and then add up the numbers, and you end up with the ratio you're supposed to have. But the other value of this is that eventually you could have to do tri-hybrids, and where you're crossing three separate traits. And here's an example. What if you did do this? It would be long and tedious, but what would you have? You would have 8 different permutations of the traits on each side, which would give you 64 squares. And therefore, your ratios are going to be in 64. It's going to be 8 by 8. That's how big the Punnett square would be. But what about, and then you'd have to go through and figure out, which of these has which 3 traits combined, and that could certainly be time-consuming and fraught with potential mistakes. So we're not going to do a lot of this, but let's suppose I said try hybrid cross, and of a so we're always going to be talking about heterozygous, right? We're talking about crossing the F1s, and so we're going to deal with the round, yellow, and whether the pod is smooth or constricted. So what is this going to be? R, R, Y, Y, S, S times the same thing. R, R, Y, Y, S, S. Here's what you should know. That if you did this, what are the odds of getting this right down there? The odds of getting any homozygous trait, for example, RR, is going to be 1/4. So then we also have, in order to get this, we have YY as well. There's a 1/4 chance of that. And to get the constricted pod, you need homozygous recessive again. 1/4 again. 1/4 times 1/4 times 1/4 is 1/64. So we can get that. And again, we're not going to do where you have to find all these things. The more heterozygous alternatives you have, the more complicated this is going to get. But what about wrinkled, which is recessive, green, which is recessive, but smooth, which is a dominant phenotype? Well, in order to get wrinkled and green, we need homozygous recessive. But smooth could be homozygous dominant or heterozygous. So what are the odds of getting these? So what's going to happen? For RR, 1/4. For YY, 1/4. And for capital S, 1/4. So for this guy, it's 1/64. But what about this? RR is 1/4. And YY is 1/4. But SS is a heterozygote. That's 1/2. So 4 times 4 is 16 times 2 is 32. So this is going to be 1/32 or 2/64. So the odds of getting this are 2/64 plus 1/64, which equals 3/64. And we could do that again for wrinkled, yellow, and constricted. Wrinkled is a homozygous recessive. Constricted has to be a homozygous recessive, but the yellow could be, we're going to get yellow whether we're homozygous dominant or heterozygous. So what's this going to be? 1/4 homozygous, 1/4 homozygous, 1/4 homozygous, or 1/64 for this option. And for this, we already did it, so let's not do the math again. It's going to be 1/32 or 2/64. So 1/64 plus 2/64 is going to give us 3/64. So that's how you can use the probabilities to find phenotype